Okay, I want you to watch every minute of this. Don't skip around. You'll get very confused. Watch the whole thing, and then if I have time, we're going to get really into some really cool experiments with this Crookes radiometer. And this tells, I can show you and demonstrate to you and literally prove the things I'm saying about the electromagnetic spectrum, and it can only be solved using electron flood theory, which says that there is nothing that is not made from these dipoles, and it's a muon and an electron neutrino. It makes everything there is. I will be very, very deeply detailed showing this, because this is the new atomic model, and we have it completely, well, not completely, but we're getting pretty close to getting it all on paper and books and so forth. And it's going to be the anatomy of the proton, the particles, the nucleus, the dark muons, the electrons, standard model versus electron flood theory, and it's going to be extremely detailed. It has to be, and it's very simple. It's as simple as you can possibly get. If you watch this whole through, and then you have any questions whatsoever, ask me. I'll be very, very happy to answer. But I'd like to have them from some physicists, some people that have some true, claim to have some true knowledge about these particles. And nobody does right now, because nobody understands them. They don't understand gravity. They don't understand what light is, what heat is. They don't understand why the cosmic radiation happens and what is going on with our atmosphere, and why is it so hot out in the edges of our atmosphere and so cold just underneath, and then it's hot again down on the surface. What's going on? They have no clue, because they don't understand. The universe is saturated with these particles, which are light, and they are particles. So everything that's in the universe we have to scrub through. Stick with me. Don't jump around, or you will be confused. All right? Stick with me. Watch the whole thing. And then the next one, we're going to get into some real deep experiments. And it's going to be a lot of fun. I can't wait to get into this part of it. Okay, before we get started, I just want to do some introductory stuff. Fermilab has found these two particles, which they call the point particle and the fixed particle. And here they are from Fermilab. That is the fixed particle, and has a glowy edge around it, has all the weight, and is just one fixed particle. It never changes size. This can get big and get small. It has no mass whatsoever to speak of, and it just has a big magnetic field, and it can get big and small. And this is exactly what we found in our experiments. This is our experiments. They see these, but they see them in a whole pile of debris, because when they smash their particles, they're smashing huge particles, and they're getting all kinds of big chunks of it. They call it a particle zoo. We started with the smallest particles that exist, that they know of, basically, which is light and electrons. That's all these are. These are two dipole electrons. It's dipole electron flood theory. So, look at this carefully. This is from Fermilab, and they say this is what they have seen all by itself, and they know it's the smallest particle that they can find that's black, and they know this is the smallest particle they can find that glows. All right, those are the two, they call them a Dirac neutrino. We found them from light. This is a picture of light. This is literally a picture taken of a photon, and that is the dark matter, and it literally is the dark matter. All right, they didn't realize it was the dark matter, because they're not looking at it as we can see it. The dark matter is attached to the bright matter. That's all. And the dark matter attracts the white matter desperately. That's what electricity is. The white getting back to the black. You have to pull that white apart away from the black to make electricity, and then it will come back into that black, and it'll go through all kinds of circuits and push motors and do everything to get back to that black. This is its normal configuration. It's tightly held. Now, when we hit the Venturi here with this light, it exploded, and it divided. The white divided from the black. We created raw electricity. That is raw electricity. And it is an electron shower. And the black is the muon, which went into a sterile muon condition. And here's how it happened: accelerating the light, turning the light itself into a photon, which is a double particle right here. That's the photon. As it's gaining energy, it's a neutrino. And I'm going to show you all that stuff. I have it all here. As it's gaining energy, it's a neutrino. Here it is right here. This is the speeding up part. All right. Normally it's like this. All right. You don't even see this though. You would never see that except it's starting to accelerate. This is the exact beginning of the acceleration phase before it really takes off. And it's starting to push all these other particles to where they glow, because they got to get the hell out of the way where I'm coming through like a freight train. And then it does. And here's the freight train right here. Boom. Coming out of here. You see this? Let me turn this light off. It makes it a little easier to see, I believe. Now, let me come up a little closer here so you can see this. All right, now, what you're looking at is that wave. And that wave, you would never even know it was there. You'd never see it, because there was a billion of them over in here and over in here, but they're not being accelerated. The only time the wave shows up is when it either is accelerating forward or being pushed backwards. That's why you see them here. They're all coming through here. You just can't see them, because they're not energetic enough. Now they're energetic. And this is when they show up as a photon. The photon is now gaining energy. It's a Dirac neutrino now, and it's going through its energy phase. It's getting brighter and brighter and brighter and brighter, and bang, right about here it becomes a photon. And the reason is it's pushing forward so hard against the reverse field that it expands to its potential as a full photon. Prior to that, it looks like this. Remember, this is where it's gaining energy, pow, into a photon, pew, exploded right here. And here's that event actually occurring right in front of your very eyes. The light is coming in here. Here it is not really configured yet. And up here you don't see anything. There's nothing at all. But there's more. There's tons of these all through here. You see them? They're up here. They're starting to gain energy, but only when they get real close to the Venturi event, that reverse EMF. So here they come. They're starting to gain energy. They're sideways, like a Oreo cookie here, and then they go sideways, and now they showed up just like they had hit the wall. That's what a photon is. When it hits a wall, it bounces. The magnetic field bounces off. That's why you get radiated back. That's the color you see. And it depends on how hard it hit and how hard the thing is it's hitting as to what the bounce back will be. This is red, and you're going to get a very dim bounce back, because it's very low energy. And I can prove this statement because I have red and green going through the same slit at the same time. You can see an enormous energy increase. Now, this is a photon phase. You're never going to see that. You never would see that, except we are stacking this up on its own self in front of this in front of this Venturi. And at this point, it's just as exactly like this thing has hit a wall. So you see it as it would appear bouncing back from a wall. Okay, this is science talking. This is not me. They're saying that a neutrino is exponentially small particle with no electrical charge. I disagree with all of this stuff. To put the remarkably small size of a neutrino into perspective, they're saying neutrinos are thought to be 1,000,000 times smaller than electrons. Well, they don't understand what an electron is, so they don't understand what a neutrino is. But they do know that neutrinos have what they call flavors. They change their energy states as they move. All right, let's just cut right to the chase. This is just wrong. Neutrino flavors are different states of the same particle gaining energy as it impacts. They say that they're different particles. Here's what they're saying about all things neutrinos. All right. Now, they're saying that the most important thing to know about neutrino is that they come in 3 types or flavors: the electron, the muon, and the tau. Well, I agree with the electron, I agree with the muon. The tau is just a variation of these. Now, here's what it says. Listen to this carefully. Each flavor, these are the flavors, of neutrinos is considered a fundamental particle. They think they're all different particles, or one of the basic building blocks of our universe. They are the basic building blocks, these two right here. That's the only two that exist, the white one and the black one. Now, they are associated with three similarly fundamental particles, the electron, the muon, and the tau. That's correct. The electron is the white one, the muon is the black one, the tau is something in between or somewhat. When a neutrino finally interacts, its partner particle often shows up, which is the black and the white. Exactly. I'll show you when it interacts and what they show up. It helps scientists identify what flavor neutrino the particle was before it interacted. I'm going to show you this right now. And they think there are three different types of particles. They're the same particles, they're just hitting harder. All right, let's just start right here. This is a pulsed red laser. It's a construction laser, and it's pulsing. Now, it's heading towards a Venturi, which is right over here somewhere. And as it's heading there, it's starting to gain energy. That's why you can see this. Otherwise, you wouldn't see this. There's a bunch of these other particles right in the air here. You don't see them. They just sort of interact with the other fields. But this is accelerating. You see how it's starting to pull to its head? Now I'm going to show you real acceleration. All right. The other wave I showed you, we were back up in here somewhere. It wasn't really even starting to hardly accelerate. It was just starting to form that wave. And what is the wave? Why is there a wave there? It's because there's a magnetic particle right in here. Magnets have fields around them. The field pushes all of these other particles. You see these little tiny white particles? Those are all gases and electrons and so forth in the air. These have to push through their fields with its field. This is the one that's the dominant field because it's being shot out of a laser. So these are reacting by a little bit of a glow, and then they have to get out of the way. This is compacting itself because it has to accelerate. That's the whole nature of a Venturi, which is here. And at that Venturi, it's total destruction of the particles. And I'll show you this in extreme detail. But this is nothing more than light. So if we can agree that a red laser is a light, which it is, and we can agree that this is acceleration, which I don't think anybody with a rational mind could disagree with that. You can see the wave is stretching right down and zip. And this is, whenever you see something gain energy, gain luminosity. Luminosity is glow. It means you gained energy. So from here you had very little energy. Here you got a ton of energy. This is exploding backwards. Remember I said there's particles all over the place in here. You don't see them because they're not strong enough. This one you see because it was accelerating. Now you see these, which are all in the air. They're everywhere because of the re-radiation backwards from this explosion. It's lighting their leading edge up. They were all in here. You just can't see them. They're all over in here. They're everywhere. They just don't have the energy. The only reason you see this one is because it was being sucked forward. The reason you see these now is because they're being blown backwards. This is, and you can see way back here, I'm sure you can see that. You see that? That's what's called reverse EMF. You see those electromagnetic force fields? That is serious explosive reaction at the Venturi, my friends. That is literally, and I'm not kidding you, I'm not making this statement kidding around. That is literally a subatomic nuclear explosion. That's what it is. A subatomic. It's not an atomic where you have a whole ton of these big things and when they go off they throw off chunks like that. That'll kill people and wipe them out. This, all you got is one. You started with the little bitty pieces. That's it. And they come back together instantly over here. I don't think there's any danger here whatsoever, because we're starting with the smallest particles there is. We're not hitting anybody with big chunks. That's the problem. And this, I went to the University of Geneva, took particle physics there. And I said we're getting these pictures using CMOS and Venturi, and I'm showing them these particles, and I'm showing them all, and I have all the particles. It's not just this, showing this here. I showed them this, everything. And here's the particles themselves. This is that acceleration phase. All right, back here, they're still not, they're like nothing. Up here, they're all over up here. But you can't see them. They have not pumped themselves up enough yet. This is pumping up, and then here, let me turn this on. They're pumping themselves up, coming through here. And you see them not in this photon phase. And just like I said before, their partners show up as they start to impact. And here is the impact not because we hit a wall, but because we hit the reverse explosion. Remember I showed you all those things lighting up in there? This is because it exploded here, sending energy backwards. So we're hitting really almost identical to hitting a stone wall here. And that's what happens when you hit a solid object. That's when you get the glow like this. But we're seeing it before hitting a solid object, because it senses like it's hitting a solid object because of the backwards force. All right, the backwards force is hitting up against these, so boom, they pop into existence. Here they're starting to accelerate and get to come up with their energy. Now the green does exactly the same thing, but where was I? Oh yeah, here it is right here. Well, wait a minute. Well, anyway, you can see this. Look, I'm here, I might as well stay here. This is the particle gaining energy. At this point, it's glowing like it shouldn't be glowing here. It shouldn't glow until it hits a wall or a solid object. It should just barely be, it should be doing something like this. This is not what it's supposed to be doing. This is way too much energy for just being in the middle of the air. It's just too much. But the reason is because of this back pressure. So it's glowing, and we can see the entire particle out here just fabulously. And here it actually splits and divides. And you can see this is a white shower. They call them electron showers, and that's what it is. The white is the electron, showers is the shower. The black is the muons, and they back right off. And the only reason we can see them here, the only reason, is because they obscure the white. You don't see them over here. They're all over here. Black is everywhere. There's black every single place here. But whenever it covers up the white, you can see that they're black. And they start to reattach right here. You would never see those black. It's dark matter. The only time we see it is because we have separated and actually visualized it in its configuration, and then its separation here, which is fission, and that's fusion. In here is raw electrons, raw energy, raw electricity. And this weighs nothing. It has no weight whatsoever. And this, my friends, if we can grab a hold of that before it comes over here, just like they do with the generators and so forth, they just grab a hold of the white and they force it into the battery. The battery gains no weight whatsoever. The battery weighs identical charge as it does to when it's discharged. No difference. No difference. That has no weight, but it has all the energy. And right there is nothing but energy. I say we harvest it here with a collector. I can't get anybody to help. I can't do it. I don't have the ability to do this myself. And I'm much too old to get involved in this. But I'm trying to point the way forward, and I've been pointing, but my finger's getting tired of pointing. So this is the particle. Once again, that's the particle gaining its energy and then becoming visible right in the middle of the air. Not supposed to happen. All right, same thing with this one. The green came through the Venturi, and you're seeing the neutrinos, and it's gaining its energy, and here it is right here. Same particle, no difference whatsoever. And this, it's now seen as a particle where you shouldn't see that. You shouldn't see that. All right, and here it is right up close and personal. And the black is the same size. Black is exactly identical, will never change sizes. It's the same size forever. The white can get glowy and small, and as a matter of fact, the green shows that actually happening. You see right here? It's coming through here. And as it moves forward, the white leading edge here is going to start to glow. The back one dims. And if you can see here, and you really look at it carefully, you can see this one here is starting to glow. And that one there is dimmer. All right, maybe it's hard for you to see, but I can show it to you in the red. And it will flip. And then this one, the dim one, will come forward, and the glowy one will go back, and the dim one will charge up. And then it'll flip again. So they flip as they go. They spin. They call it the muon wobble. Okay, just so you understand, these are the exact same particles they see at Fermilab, the smallest particles they can find, which is this one here, never changes, but has this glowy edge around it. This one has no weight whatsoever, but can get big and small. This one can't change size. It's just one fixed size, and that's the dark matter, the black particle, the muon. This one is the electron neutrino. This is muon neutrino, electron neutrino. And that is precisely exactly what I'm showing. Now, here we can see the two different energy levels. It's very hard for you to see it here. But when you see it with the colorized version, you can see this one here is getting more energy. And it's banging into these little particles in front of it as it goes forward. All right, don't forget, these are the same particles at Fermilab with that glowy edge around it. We have the glowy edge around ours. And the white one gets big and fluffy and small, just like he says. And this one never changes. All right, and this one here is banging into these particles in front of it, gaining energy, and it will flip, and this one will come to the front, and then that one will gain the energy. All right, and here's where it was at the Venturi, where it's split. We call it fission here, fusion here, and here's where we have the black and the white particles, as I just showed you and talked about a minute ago. And this is the electron shower. And this is where we should be harvesting that energy, right here. And if you read up on electron showers, they can create trillions of electron volts here. And we did it for nothing. We didn't have to do any kind of generator or anything. We just shot the light in and let the Venturi separate it out. This is just flawless as far as I'm concerned. All right, this is the particle showers. These are the electron showers, and the muons stay back. The electron showers come through and are completely separated into extremely high energies. These showers are extremely high energies. And this is what Lawrence Livermore is trying to do as well. These are electron showers right here. High energy. The muons back off. And that's what I was showing. I think I showed it. Well, it's right there. The laser comes through the Venturi, and all we get is the white showers coming here. The muons back off, you see it? And that's exactly what I'm showing here. And this is real life. This is not some drawing. This is light coming through here, and we can see it with the CMOS. Rod Warren did this, a fabulous job. I mean, he spent years doing this. And he's disassociated himself from it. I'm not sure why, but he deserves all the credit for this, discovering this. It wasn't his intention to do the atomic physics. That was my side of it. But he did all the experimentation. A fabulous job. So, again, this is just raw energy. Well, what does that produce for us? What does electron showers create? It creates raw electricity, which is what we want to run everything on now. And and we can carry this around in a little lunchbox. All right, here's what it would look like. Something like this. You put thousands of these little lasers in there. and have them dumping their juice right into wherever you want it. Have you all kind of outlets, and you just carry it around if you want it. And something very small should be able to power a car or a house or anything, because we just have 100% raw electricity. That's raw electricity. And these things are microscopic in size, basically. All right, you use a little bit to keep the thing running, and you're just off to the races. And then hopefully we could cut back on all these batteries they're making. I mean, and you see what to create lithium they're using up all that water. They're using all the water up to process this lithium. This is not a good situation if you can continuously harvest energy right off of the lasers. They just run, and they never have to stop. It's not like you get a pulse and that's the end of it. They just zzz all day long. And these are solid state. They hold up pretty well. And I need a little research on it, a little engineering research, but I don't think much more than that. And then at the device here, something like this. And I have all kind of other devices where you have a big round collector, you collect everything. But this just gives you a quick thing. This would be just like a solar panel here. And right after it comes through, we put the solar panel. Now, I would change this around, a design so that the beam went into the center before it hit the venturi, and you harvested all the white. But that's, there's a lot of things to be determined. But the whole end result was you just push this white down into your battery, and you're off to the races. And you could have a lot of these devices in one little box. It doesn't take much of this white juice. It's amazing how long things will run on these little tiny batteries. I mean, just to run forever. How many electrons can you be pushing out of some little tiny thing? To me, it's mind-boggling, to be honest with you, how much electricity you can get from these little tiny batteries and so forth. Now, this looks like it's just squirting out gobs of it. So, I don't know. It needs to be engineered, looked at by MIT or somebody that really wants to do this, the Jet Propulsion Laboratories or Fermi or whatever. But somebody's got to really look at it. This is not pie in the sky, my friend. This is quite real. All right, this is why this is so important. They're trying to work with these huge proton colliders to get these end result of electrons. We don't need to do all that stuff. We started with the neutrinos, and then the neutrinos just automatically show up at the venturi. So we went from a few million electron volts up to hundreds of billions or even trillions of electron volts, depending upon the type of energy we start with and the design of the venturi and how we harvest it. But we're starting out with literally millions of electron volts, which sounds like a lot, but it's not. It's not very much at all. And if we end up getting from those millions hundreds of billions or trillions, just think of the increase in energy. It's an enormous increase in energy. So a very small device should give you a lot of energy. Electron showers. These are electron showers. This is the physics of electron showers. It's an increase of energy that is astronomical. All right, these electron showers, these particle showers, they're not unknown, but they're primarily considered to be from cosmic radiation, which is these extremely high energy particles that they're not normally seen here on Earth. They come through the atmosphere, cosmic rays. Well, we're shooting this light, creating literally cosmic rays. That's what it's doing. All right, if a cosmic ray creates particle showers, we're creating particle showers. So we're basically doing the same thing as a cosmic ray would do, creating these particle showers. And these particle showers are extremely high energy. All right, here it is right here. Air showers of the cosmic radiation consist of a cascade of subatomic particles, these little bitty parts I'm showing you. and electromagnetic radiation resulting from nucleon-nucleon collisions of high-energy cosmic ray particles from space with atomic nuclei of the Earth's atmosphere. They're talking about atomic nuclei. I don't have to get that. I can get electron showers by using light. They're just trying to do it with the big particles and using the too big of particles. And then they get all kinds of nuclear debris, which is broken. Okay, my friends, let's get right into this. He's talking about the periodic table being wrong. The element doesn't fit the periodic table. Well, I have a whole new take on a periodic table. So this is the size show. And again, I think I've explained a lot of what I wanted to explain. Let's see what he has to say about hydrogen and the periodic table. Here we go.
At hydrogen. It's probably sitting up above lithium at the top of the alkali metals. But look a little closer. Maybe it's shaded a different color than the elements below it. Maybe it's floating a slight distance away with a little drop shadow. It looks like it's embarrassed to be there, like it's not really with those guys. This isn't a graphic design mistake. Even though it's the simplest element, chemists actually don't agree on where hydrogen belongs in the periodic table. There are at least 3 credible places you can stick it, and that's a problem for our understanding of how elements work.
Exactly. They don't work. They don't work as advertised. Now, I don't know what he's talking about being, it is a different. Hydrogen is the smallest stable element. All right? And it's semi-stable. If you put a little spark to that, it explodes like an atomic bomb, literally, because every single electron in there disassociates and separates. It just makes a gigantic explosion. All right, just remember this. He's going to explode this hydrogen and oxygen, and it's going to explode like an atomic bomb. He's telling the kids to open their mouths so their eardrums don't blow out, and they think he's kidding.
If that sound was too loud for you, keep your mouth open, because then the pressure in your mouth.
That shook him up a little bit. The kids are loving it. Now, there's no other element that explodes like that. You can't put a spark to anything here and explode like that. That was just off the charts explosion, and it's the smallest particle there is, or the smallest element. And what happens is every particle that makes that up, which are all dipoles, all disassociate at the same time. And that's what an explosion is, just an expansion of all of those gases taking up their own individual places in the universe, instead of all being glommed together in a tight atomic bond. Now they're separated. All right, they're just trying to make justifications for why hydrogen is a metal, actually, and not a gas, and all kinds of silly arguments, because they have these designations of what all of these elements fit into, whether they're alkalines or alkaline earth metals or transition metals, other metals, metalloids. They give all these different names they give them. All it is different quantities of electrons with different outer shell bonding capabilities. They call that ions. The ions are with extra electrons or not enough electrons. All right, those are isotopes. When you throw in extra electrons or you take a bunch of electrons out, you end up with an isotope. It's not actually the element. So carbon has I don't know how many different ions, literally thousands, I believe, because every one of these is a different number of electrons. And when you look at all the isotopes of electrons, it's incredible. All right, I think I probably showed before, or maybe not, but carbon is right here. That's all it is. It's all these different carbons are still carbon. Why are they different? Carbon 8, 9, 10, 11, 12, 13. The only ones that are stable completely are 12 and 13. Well, 12 is exactly totally stable. 13 is 99% stable. And all the rest of them are either they want to gain electrons because they're less weight, see 8, 9, 10, 11. Then when it hits 12, it's stable. It goes to 13, almost stable. Then they go above and their isotopes, 14, 15, 16, 17, all the way down the line. And that's because they just have more electrons than they should to be perfectly stable. So they will give some of those up and attach to other things to sort of slough them off to the side to stay stable. But it's now in a bonding configuration as a molecule instead of a lone carbon. A lone carbon is exactly stable at 12. Right here. That's it. It's stable. It's not going to try to gain one. It's not going to lose one. But down here, it wants to gain some to get up to a 12 nucleus. Over here, it's got too many. It wants to give some up to somebody else and still stay attached in the group. That's what a molecule is. I hope that makes sense to you. All right, I was just showing you isotopes, which are nothing more than ions. And he's talking about hydrogen forms similar ions to halogens. It's just all terminology at this point.
Can also form similar ions to the halogens. You can get hydrogen to gain an electron and make a hydride ion H-. And halogens also make ions with a single negative charge, like F- and Cl-. Hydrogen, fluorine, and chlorine also all make gases at room temperature and all exist in diatomic form.
Diatomic form, which means the two of them together, attached together. Now, they get stable in these particular ones, but normally they're not stable when they attach together. They'll want to attach to something else. Gold is a diatom.
F2. On the other hand, hydrogen differs from fluorine in a big way, in that fluorine is the most electronegative element on the periodic table, meaning the greediest and most likely to hog electrons from its bonding partners. If hydrogen were placed above fluorine, you'd expect it to be even more electronegative, but it's actually much better at sharing. That brings us back to group 14, the carbon group. Carbon and hydrogen have very similar
hydrocarbons. That's what life is made out of, is hydrocarbons.
Negativities. They both tend to make similar sorts of bonds, including with each other, and they can participate in similar reactions.
Okay, that's called a nucleophiles invade other elements. As your life goes on, you're changing the molecules in your body continuously, 24 hours a day, just continuously. And what happens is certain electronegativities and so forth, particles move in and they say, here, I'll give you a couple of these electrons, you give me that oxygen, or give me that carbon, or whatever it is. And they jump back and forth. And then these primarily transition metals continue on until they go back and they work with enzymes and chemistry in the gallbladder and the liver and the pancreas and everywhere else. And they clean all that stuff up. And then they get it back to where it can accept or give up electrons. And then it goes through the body and moves different molecules into, your body so that you can absorb nutrients and oxygen and all that stuff. It's just a continuous replacement of electron polarities, all right, to the matrix of your body. It says, hey, I need some oxygen over there, I need some glucose, I need some of this, I need some iron, I need whatever it is. And they bring it over and they deliver it. That's all it is. That's how your blood works. And this is basically what your blood is right here. Transition metals. There's everything else too, but these are the ones that do the transitioning of molecules. They bring the parts down, and then wherever they're necessary, they use them, and then they transition into something else, go back and get cleaned up. All right, so that's the kind of reactions they participate in. And hydrocarbons are the biggest thing in your body, basically.
But some people will step back and say that comparing an element with one outer electron to one with four just isn't actually the same thing at all.
All right, let me just tell you right now, nothing here is the same thing at all, because right here, for hydrogen, you don't have one big ball in the center, just one big solid positive and one little tiny negative. You have about 1,825 dipoles. And what happens is you hit a certain number and it's stable. And remember I showed you in the carbon you can have extra particles and you can have not enough particles. If you don't have enough particles, it will want to take one on or take more than one on. It depends to get to that correct number. If you have the correct number, and then you have one more that wants to get in to the black, because the black is much more attractive. It's just unbelievably attractive. So they want more electrons will want to get in there. And that's where you get your quantum states, where it says, no, you can't get in here because we have enough. We're perfect. We have just enough to coat this ball. Nothing more is needed to coat this ball. But you can stay that far away. So it stays out there in that quantum state, but it's still a dipole. And these are all dipoles. That's all it is. And the bigger this one gets, the more you get in a cloud. And as it gets bigger and bigger and bigger, you get more and more and more out here that still want to get in. And they're the ones that do the bonding. All right, so consider this to be just nothing but that. And then there's some extra ones out here that really want to get in. This says, no, I'm perfect. I'm good. I'm good. You can't get in here. You just can't get in here. Stay out. Get out. Go, go, go. And they say, well, I'm going to come in. I'm going to, no, you're not. You can get just right to there because that's where you hit my field. And then this one will hit this guy's field. So he comes in, he says, I want to get in. He said, no, no, no. We're okay now. We're coding here. You can come in, but you're going to have to stay there. So this is real tight. These are tight, tight, tight. These are a little looser. And the bigger it gets, the looser they get. On the outside, they just barely held on. Now, I think I probably showed you this already, but I've been doing this for a couple of days, so I forget. A day or two ago, I started this, so I may not have shown you this, but this is my model of the atom. All right, there's going to be a dark black core, which is those dark particles. And then there's going to be the really glowy, burny parts. And the closest ones are tight and blue. And then green is not quite as tight. And then red is the loose ones. Now, there's this configuration and then there's this configuration. It's one or the other. This is the other configuration where you got black, a core, and then it's really tightly held with the blue. And then there's another black set of particles hanging onto the blue, and then the green are hanging onto the black. So you're always going to be going out, and the red is always on the very, very outside. And again, this is the anatomy of the proton, and these are the only two particles that exist. And this is going to have a glowy edge around it depending upon the color of the electron, which is the energy level of that electron. And these are the differences in the standard model. The standard model just says that there's a big positive core and little tiny electrons. It's just not the way it works. There are positive particles and there are negative particles. That's all. And this makes a ball of positive with the electrons, the same number of them, coating. And every single, what we would always consider was an electron, or gluon, is both black and white. Dirac Neutrinos, basically they call them, and they're correct. They're the smallest particles that exist, and they have an antimatter and a matter particle, if you want to call it that. I call them a plus and a minus. This one does all the explosiveness, and this does all the cold and banging around. That has no weight, and has all the energy. This has all the weight and no energy other than that it pulls that white down to it just absolutely incredibly. And it's unstable. This always wants to attach to something, be heat or energy. All right, this is stable. Photons, the smallest particles that exist, is two of these back to back, and it gets one big cloud of a field around it, so it can bounce away from stuff. It's still stable. This can't bounce. This goes in, bink, it grabs and holds onto something, or that one holds. You know, it depends on what it's hooking up with. It either becomes heat, or it becomes incorporated into something as a extra electron to make some exotic molecule. I guess that's all you can think of it that way. And neutrinos make everything. The neutrinos are all the different phases of the colors, basically. I think I've explained the neutrinos. Okay, this is the Crookes radiometer. Nobody's been able to figure out how this works for 150 years. They know what happens, but they know it's caused from thermal transpiration, they call, and I'm not disagreeing with that, but I say the cause of everything here is the glass, and nobody ever talks about the glass. Now, I'm going to show you what happens when they put light on this. All right, there's a black side and a white side to each one of these 4 veins. All right, now I'm going to shine light down on it. All right, and watch what happens. The black side should start to move and push forward. You see it does start to spin? All right, let me come down here. You see it? The black side is pushing this way. No matter if I shine right directly onto the white, it doesn't matter. The black side still pushes, no matter if I beam it right down onto the white. The white is actually being sucked to the light. The black is also being pushed away from the light. How can I explain both of those things? Well, I'm going to explain exactly why. Light is made of black and white particles. And one pushes and one pulls. And that's what we got going on here. We got both of those things happening at the same time. And the reason is because of the glass. And you say, well, what's the glass got to do with it? Well, let me explain. All right, now if I put cold water on here, that thing would turn around and go the other direction. Why is that? Why would cold force it to go this way? So obviously it must have something to do with heat making it go this way. All right, and I again say it's because of the glass. Okay, my friends, before we get into this, I just want to explain to you what I am hoping to show. That the standard model is not correct. Everybody knows it's not correct. They can't predict gravity. They don't know what dark matter is. They don't know what the nucleus is made out of. Here's what the nucleus is made out of. It's dark matter and a glowy matter, which is the energy. So the dark matter has no energy whatsoever. It's just a bowling ball. And that sucks the white particles into it. And there's only 2 possibilities that I can come up with. And everything's made out of dipoles. It's called dipole electron flood theory. So instead of being one big solid core of an atom in the center and a few little electrons, it's 50-50. There's the electron part, which is the electron neutrinos particles, and then there's the positive muon particles, negative and positive. And these consist of different energy levels, the negative ones, but they surround the dark. Now, there's only one other possibility, is that they're layered like this. So the dark, and then a layer of the electron particles, then another layer of muons, and then another layer of electron particles. But there's always the last layer will always be the electron particles. That's why we never could see the dark matter, because the only time you can see the dark matter is from our experiments, as you will see. And they see it from CERN too, but they in Fermilab, but they don't know where it came from. All right, they show it, they just don't understand. Well, here it is right here. Let me see, hold on a second. Okay, my friends, I need to prove dipole electron flood theory in every single possible electronic interaction. And that means everything that happens. 100% of what happens I have to be able to explain. And I'm serious. And I call it dipole electron flood theory. What that means is all particles are made of dipoles, which are bar magnets basically. And the core of the nucleus is not, as they say now, with one huge proton and one tiny little electron for hydrogen. No, it's 1,825 or so of these dipoles. And they might be arranged this way, or they might be arranged this way. All right, where all the energetic particles surround just one little black core. Or they could be a black core energetic, another black layer energetic, which is this other style. This I'm not sure of, but the outside layer of every atom, every single atom on the periodic table, the outside layer is going to be composed of these energetic particles. All right? And they are going to be the ones that stick to other particles to make molecules. And that I can also explain, all of that stuff. The only two particles that exist is the white glowy electron and the dark muon. Now, the electron portion can get a whole bunch of different energy levels. The dark muon doesn't do anything. It's just a bowling ball. It has no energy to speak of other than an extreme attraction for the white. Electricity is the white particles all by themselves being pulled over to a black ground. Black is the ground. White is the energy. So when you take a battery, all you do is fill it up with this white stuff. All right? The battery weighs a pound. You fill it up charged, really full charge, it still weighs a pound. You use all that electricity out, shooting it over here to drive your car, whatever you're doing with that. It still weighs a pound. Empty or full, the battery never changes weight because all you're doing is pushing the white in. And we can do that now with our experiments. We've shown how to separate the white from the black. And it's not hard to do. It's very, very simple. And these are what all particles are made out of those two particles together. And 1,823 of these together make up what they would consider to be a proton. 1,824 would be a neutron. So all it is a big bunch of little particles. That's a proton versus what they say, this is a proton. And they can smash this to bits. And they see these little tiny particles. They see these exact same particles, but they just come out in a mess, so they don't know. We started with light. So we started right down here. All right, we started with that, just like that. And so we can watch them manifest and all that, which I will show you all this in extreme detail. And of course, the neutrinos are, as advertised, they are different flavors, different energy levels until they become fully photons. We're going to go through all of this stuff. All right, and this is going to be the changes to science, the changes in chemistry. It's all changes. Everything changes. This is no longer valid. It's just not valid at all. Hydrogen is not one big proton and one electron. It's 1,825 or so little bar magnets all held together. And at that exact quantity, and there'll be an exact quantity of these particles, they'll say, okay, we're stable now. We got exact correct number. Don't take any more on and don't give any up. That's what an atom is, and that's what's called the stable one. Carbon, though, has like a bazillion different isotopes, but only carbon-12 is stable. Carbon-13 is 99.99999% stable, but then there's a whole ton of other carbons. They're not stable. They have half-lives, so they're still carbon. That's the key. They really don't understand the periodic table. There are so many extra particles inside of every one of these protons, they just never considered it. Helium is 7,000, almost 8,000 particles. It's not just 6 or whatever. And this is not just one, it's about 1,820, whatever, somewhere around 1,825, something like that. All of these, every proton adds 1,823, and every neutron adds 1,824. And up in here, you got zillions of protons and neutrons that make up, and they say, oh, it's 25 particles. No, it's not. It's like 50,000 almost. All right, there's almost 2,000 for every single particle that they say. Hydrogen, like I say, is 1,825. That's almost 2,000 times bigger than what they would tell you, or what scientists currently feel. So this is all changing, and I will show you how it changes. And we're going to use this little light mill, and I'll explain to you these particles and why this light mill works, and why it's white and why it's black in the light mill. And nobody's been able to figure this out for 150 years, and they still don't know how. And they say, oh, well, it's thermal transpiration. Well, explain exactly what it is. And I'll tell you exactly what it is. What's causing this is the glass. Nobody's ever even talked about the glass. That's the problem right there. And I can explain this very, very simply. All right, so don't forget, we got the dark core with the glowy edge around it, and that could be green or it could be red, it could be blue. And here is the glowy part that is attached together. It's what you see right here. They call them Dirac Neutrinos. Now, this is a stable particle. The photon is the smallest stable particle there is. That's why it bounces off a wall and you get a light, bounces into your eye. It's stable. Electrons are not stable. Now, this is when we accelerated this thing like crazy. And you can see it's pulling itself just like a jet fighter right out of its own magnetic wave. And here it's just literally, and I am not kidding whatsoever, this is a subatomic nuclear explosion. All right? It creates fission and fusion. And here is the fission and fusion right here. You saw the black and the white particles are attached together. And the only reason you see that black, the only reason you see it is because it's obscuring the white. The black doesn't emit, it doesn't absorb, it doesn't reflect, it doesn't do anything. The white seeks the black and it coats the black. All right, and it will grab right back to that black instantaneously here. And that's called an electron shower decaying or actually reattaching to the black. And this is when it forms the Higgs fields. The Higgs fields are here. And I can show those too. All right, here's the Higgs fields. Remember, here's the Venturi here, coming straight through. Looking into it, we see this, Higgs fields. We're looking straight down into the Venturi, and all these Higgs fields are this is when the white particles, you see all these little spritzes? Can you see that? You see all those little spritzy looking things? When they shoot up here and they hit the edge of these disks, they start to spin. They grab the hold of a black particle and they're spinning. That's what a Higgs field is, and we can create these in billions per minute, trillions. The green does the same as the black, only it's a lot more energetic, and I can show you that in a little better detail. But you can see all the black particles are coming this way. They've been separated from the white particles. Only the white is coming this way. You see it? Only the white. This has black and white because the Venturi is a little askew. But you can tune this. You can tune this all kinds of different ways. And you can design that Venturi in all kinds of different ways. And this one here, you can see these little spritzes. Every one they're hitting. And that one there is a reverse particle. That's very, very unique. And I think that created something that very, very strange. I can show it to you, but I won't right this moment. Now, I can show you right here the green and the red coming through at the same time. And you see how powerful the green is compared to the red. You see how dim the red is? How powerful the green is? And the blue is much more powerful than that. Because those are the energy levels that are required to rip the light particle, which is the photon, out away from the molecule, which is the crystal, and shoot it off. And certain crystal, which is the blue, is very, very fast and very powerful, and that creates a lot of havoc. And it's a lot more strong. As you can see, this really won't hurt you. This, you know, for a long time in a certain area. Blue can hurt you, and then you get up into your gamma rays and X-rays and all that, which is nothing but the black particles. There's no more white particles left, and they will just tear you up and kill you. All right, this shows a few things at one time. This is blue laser, very, very fast, and you can see it's a beam of light. And it's spinning, and it's actually spinning to the right, which means it's drifting to the left as we take that, and that's all one particle, and it's showing up in all of these different, like strobing. Now you can see it's very, very fast and compact here, and it's just slowing down as it comes out. So light can slow down, light can speed up, as I showed you with the red. Light is made of these particles, and you can see there's two of them here. It's only showing like one here because it's just too fast. It's just way too fast. The red and the green are different. All right? The red, as you can see, it's not even close to the blue. Very spread out. So in other words, here's what you got. Think of it this way. This right here is the wave. All right, so there's a particle here, and then there's a particle way over here. So this wave is way out here. Now, you look at the blue, and it's like way down here. You see it? That's what's called red shifting. It's going from the real tight blue, drifting back down to red. And eventually, in outer space, space is filled with particles. It's called the quantum foam. Eventually, these particles are going to just slow down until they stop. And that's what's called the cosmic microwave background. And it's just particles that just, it's not moving anymore. And that's what happens to light. So light coming from way away from us to us is not going the same speed. It's obvious it can speed up and slow down, and there are variations of energy. As you can see here, it is. It's the same particle. This phone didn't have the same. This was Fabien Boulay. I could easily over in Francais. And Rodney Warren in Australia did 99% of the other pictures. And Rodney came up with the Venturi effect, just pretty much accidentally, just playing around trying to do a double slit. And he did a single. And what he ended up having is a Venturi to force the fields to come in here and only let the white through. And when I saw it, I freaked out, and because it explains atomic vapor, which is in 1970 I wrote a paper saying light is atomic vapor. Light is atomic vapor, and that's all it is. And that vapor condenses into what we call atoms and elements. All right, but it's still made out of like little particles of dipoles, which are, again, I showed you somewhere around here, the ball of particles. All right, so when this comes through here, we're down here. And it just breaks these two apart. We get fission. It's still fission. I don't care if it's a big, gigantic thing and you get fission, or it's a 1 or 2 and you get fission. It's still fission. And that's fission. And that's a sterile muon, a black ball. And the reason you see it is because the white that would normally come at us is just, it's blocking it. It's just blocking it. They're all over the place here. There's black everywhere. It's black everywhere, and you're never going to see it. That's why it's dark matter. Because if it's attached to other molecules and atoms, it always coats them, which is what I showed you in our atomic model, which is here. All right, so you're always going to have the glowy stuff out here unless you break it into little bits and pieces, which we did because we started with light. Not protons. This is a proton. This is a monster. It's gigantic compared to what we're working with. All right, and when they splash, they get all this stuff, and then they dig through it, and they call it a particle zoo, and they dig through it for 10 years looking for stuff. And all there is these two things. And they're in different phases. And I show all those. I very clearly will show you this. And we will be having a book to try to explain this, because everything has to change 100%. And I'm not kidding you. Somebody put in a question to AI and asked if I was correct about what I'm saying, what would have to change. And they said everything would have to change. 100% of what we thought about matter would have to change. And what it does, you're starting with all new, different configurations. This is how life can facilitate all of these chemical changes happening in your body instantaneously with enzymes, because in between every one of these particles, there's thousands of different points that can make and break, and that's what an enzyme does. It breaks and breaks things millions of times a second and ends up with a chemical that you need to make your body run, or in nature. That's how it works, enzymes. Enzymes are made from bacteria. It's a very elegant system, but nobody's understood how the basis of it works until now. It's a dipole electron flood theory. And this Crookes radiometer is going to be a lot of fun to play around with. I've already played around with it. It's a lot of fun. And you have to understand the pressures. This has to have a pressure in here that's very, very low, but you still have to have molecules in here, but not crushed together. This is the thing that they don't really understand. I'm not kidding you. I know it sounds crazy. I know it sounds insane to say this, but if you look up what heat is made out of, and they'll say it's vibrating molecules. Well, what does that mean, vibrating molecules? Why are they vibrating? If you just have something sitting on a counter and it's hot, is it vibrating and then it gets cooler? Well, to some degree, I suppose you could say that, but it's actually excess electrons in there. That's why it's heat. And if you put it in cold in a room, it will absorb those extra electrons into it until everybody's not pushing or shoving each other. So you could say it's vibration. It's vibration. It says, hey, I'm cold. You guys got a lot of extra electrons. Let me have some. And they just move in there. And as it absorbs those electrons, it gets heavier. It literally gets heavier. Even though it gets hotter, it literally gets heavier. Electrons have weight because they have both the black and the white particles. All right, a gluon is the same as an electron. An electron is a gluon. And that particle right there has the weight. And it's approximately 0.000585 atomic mass units. This has no weight whatsoever, zero. It has all the energy. All right, so we're gonna get into this deep, and this changes everything in physics. If you want to get into physics, now's the time to do it, because chemistry and everything, all of this has changed now, which leaves open room for somebody that really wants to pay attention to the new stuff to put their foot forward and say, let's look into this. Let's do some research here. Let's get some funding. That's what it's all about, is getting funding. And when the people that have the vested interest in it to say, we know everything about this, they say, oh, wait, guess what? We didn't know anything about this. Can we have some more money? They're going to just say, well, they nibble around the edges. Well, no. And that's what I'm seeing right now. And it's every day, it's the same stuff over and over. And even like this is long ago. This is 10 years ago, more than that. But I tried to work with these people then. And they were talking about the quantum foam, which I also agree with. Light. I did a video about this at the same time frame. And I said light is dark matter on its way to hitting Earth's atmosphere. You don't see it because it's dark until it hits something. That's what light is. It's just nothing more than a particle that's moving through. If it's a vacant gas is in space, there's no gas whatsoever, there's still going to be magnetic fields and everything else. That's what the glow is. And the quantum foam says just exactly what he says here. Well, first of all, he says that the fixed particle has a fuzzy edge around it, but it's just one size, fixed. The other point-like is an abstraction. It has zero size, but it has an extended field. Exactly. That's exactly the white and the black one. And the quantum foam, I also agree with this 100%. He says empty space isn't empty. All right? And it's a dizzying display of change. These particles are subatomic particles winking in and out of existence. These particles are real and have an effect, yes, because as the other particles coming through from the sun and so forth, they're clicking them, hit them. Every now and then they're going to hit another one, and click, 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 and you see these splash, boom, boom, bing, boom, 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 boom. At the same time, these are slowing down. And there is huge fields in space. If they don't see these, I don't know why. This was taken with a cell phone. Hold on. You see that? These are the fields that are in space. If these particles are coming through these fields, and these particles are magnetic, these fields are also magnetic. So you're going to have push, to bounce, to shove, to boom, to boom, to boom. We have no idea where things are out there. They think it all is coming at the same speed, never slows down. Totally wrong. It's going to come through here, and we're going to have all kinds of slowing down. And that's what it's all about. And you see all these things are dipoles. They're all, basically everything's a dipole except the moon. The moon, when it spins, it makes itself into a dipole. I can explain all that too. The moon, though, is crushing the light in front of it. It's moving this way, causing this not to shift red, but to shift blue. So there was just normal light here, but it's pushing into it, forcing it to go downwards. In other words, out here, remember the red was way out here like this? Well, we're pushing into all of these particles that are pushing against it, which is sunlight, and it's forcing it down here into the blue range. So that's what that is, as far as I'm concerned. I could be wrong about that, but I don't think so. And the other one, here's another one. This was taken with a cell phone. You see that? I think this is Venus. And I think it's Venus for two reasons. It's extremely dipolar. And it's spinning backwards. Venus spins backwards. So it's going around the sun this way, but spinning the wrong direction from everybody else. And it has two magnetic fields. You see that? There's another magnetic field running right down the pole. It's got two magnetic fields, and this is just staggering amount of dipole nature to that planet. I'm pretty sure that's Venus. But I can't be positive of that either. Somebody just sent me this. It was Dylan Carpenter. He's Rod Warren's nephew from New Zealand. And I only had contact with him maybe once or twice, and then I lost contact with him. So if he would contact me back, I'd love to find out exactly how he took this and if he's got any more. And Rod I've sort of lost contact with him too, because that goes back 10 years almost now. Well, it could be 10 years. And so anyway, this has to be understood for us to move forward in physics. It really has to be understood. Everything's made of dipoles. Okay, I think I showed you quite a bit here. What we want to remember is that CERN and Fermilab and all the super colliders are starting out with protons and neutrons, which are like this size. They're like this, smashing these together, and then they're finding all this debris. All right, they think they're just one big solid thing, and they can break it into, and they call these a particle zoo. Yeah, they could just got all kinds of pieces of this. We started with that. So we started with these little particles here, and then we split those apart. And then those split apart themselves. So we ended up with half of one of these. They end up with this. A chunk like that, they call it an X particle. Another one over here they call some kind of other particle. Another one over here, but they end up seeing these little bits and pieces. That's what they're looking for, is the tiniest bit that exists. And that's what I just showed you, the tiniest bits that exist, and they can be separated. This is very top-end stuff. These are the tiniest bits in a light. That's light. That's a photon. And then we not only had them here, we split them into what they know. They call it the muon. They call it electron neutrino, and we did. And then not only did we do that, that's fission, that's fusion. This is raw electron showers. This, my friends, is exactly what you need to do to create electricity. You need to break the the black off of the white and force the white into a battery or whatever. Now, we can run this all day long in the same device, right in a box, and have literally thousands of those squirting out that white stuff. And I'm telling you right now, I don't see any reason we shouldn't be able to create enough white stuff in a little box this big to run a car. That's my guess right at this moment. This is huge amounts of white juice. You see this? We didn't have to do all of these gyrations, creating proton-proton collisions, hadrons, decaying this and that. We started right down here with the neutrinos. I just showed you them, muon, electron, neutrino. We split them, which caused to create up to 100 billion electron volts, all the way up to trillions of electron volts. And we are starting out with millions. Millions seems like a lot, but it's nowhere. When you get to 100 billion, that's a lot more than a million. And that's what the increase in energy is when you can get down and separate these white particles from what they consider the black particles, which were the protons. Because then all you have is the electrons, which is the white ones. They have no weight whatsoever and all the burn. And that's exactly identical to what I show you right here. All the weight is in the black. It doesn't get through here. This is all the burn. And we can send that juice right down through a device similar to something like this. You shoot the laser through there. The black can't get through. You have to tune this correctly, and then you just let the white get through, put it into a harvester, send it down through a photodiode, do whatever you want with it. Put it in batteries or run a car or whatever you want. And there it is right there. But you got to get it before it hits the black. Right here, there's no weight whatsoever to it. It doesn't weigh anything. And you just let it go down into a battery. This is going to slap it in there, the black. Bam, bam, bam. You have a pulse laser. And every time it hits it, it squirts, squirt, squirt, squirt. You let it squirt down through a photodiode and do whatever you want with it. That's electricity. Right now, we have to rip that white one away from the black one, and that requires a lot of energy. We just shoot it through the Venturi. All right, this is just like a little mock-up I made. This is a Geiger counter, but something this size, you could have zillions of these literally inside here. I don't know how many, but these are microscopic. And you just have to have it set up in the right configuration where you could harvest a whole scat of these things. What that looks like, I don't know. I don't know how much you could get out of that, but I'm going to tell you what, that is some serious amount of energy. And it's only the white, and that is all you want to come down through like a photodiode. So your laser shoots the stuff, all the black stuff pushes the white, and bam, 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 bam. Squirt, 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 squirt. Harvest, 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 harvest. Gate, 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 gate. Do whatever you want with it. After that, it's all off the shelf. And this is all off the shelf too stuff. This could be done overnight almost. Okay, you know how I'm always bragging I've taken all these courses and so forth? Well, I have. And you can take them for free. This is University of Geneva in Switzerland. They're right next to CERN. And I went there before and I was looking up, I was going to take another course there just so that I could interact with the professors, not so that I could learn something, because I'm telling you, I know more than they know, and I'm telling you, that's just a fact. But you can enroll there, and then they have another, and that's the University of Geneva, right? And that's where I took particle physics years ago. And I explained to them exactly what we're doing, that we were using CMOS and we're focusing, and they listened, and they were very nice to me. And then they actually, CERN, they actually shut down for 3 years. They put in focusing magnets and hardened CMOS to see. Before they were using instruments, they were shining either energy in or putting something in there to take energy out. When you do that, you disrupt everything. You can't interfere. You can see the light coming out and look at it, yes. That's what CMOS does. They said, no, you can't use CMOS because it damages. I mean, the particle reactions damage the CMOS. I said, well, you're using protons. We're using these. It doesn't damage. The CMOS is made to work with these. They're hitting them with something like this. Yes, it's going to help. That's going to destroy it, no question whatsoever. So anyway, they did something. They made it hardened CMOS. I think they must have put layers of filtration or something there so that they take out all the big particles before it hits. But anyway, that's you can go to all of these places. I'm telling you, Coursera was fabulous. Look, this one's over at the University of Maryland, University of Colorado, University of Tokyo. And these are places I've gone, a lot of different places, because you don't have to pay. It's free. But you don't get any certificate. Nobody gives you anything. But you put it in your own book. You know, make a book like this, something like this. This is just trash, you know, it's just something I can play around with, because I don't have to go impress anybody. But if you did this right and did it with a nice clean book and wrote all your stuff down and everything, when you go out to get a job, you say, hey, I went to University of Geneva, particle physics, here's my papers. That's what I'd do. You know, the actual truth of the matter is the best thing you could do is to learn from what I'm showing you from our experiments and do some experiments on your own. Get your hands dirty. You know, I did some of this stuff, but Rod Warren was the guy he was just fabulous at this. But I didn't put a lot of time into it. It's not a complicated thing to do. All this was two actually nails. They were finishing nails right next to each other, straight like this, shining the laser through it, and this is what came out the other side. And he used this. Well, here's the phone he used. I did the same stuff. Hold on. Here it is, right here. This is a Galaxy Samsung. I'm sorry. Yeah, Samsung Galaxy S3. This goes back to 2012, I think, or maybe 2014, I can't remember. But it goes way back. And he used the selfie side. And I did some myself. I was terrible. It takes a long time to do this. This is not something you just knock off in 5 minutes and go home, have a nice dinner. I don't know how much time he spent at this, but I worked with him for 5 years at least. And he never got anything for all his work other than to do this and, you know, and help me discover electron flood theory. Now we're going to have a book that will show all of Rod's work here, because this is just nothing. I got stacks of things from him, and I have things that nobody can explain right now, like this little particle right here. That little particle right there, you see that? All of these are Higgs fields coming out. And you see these little spritzes of light hitting, and that's what causes the fields to start spinning, is when the white particles turn back into black and white particles. That's what Higgs fields are. It's not the other way around. They say the Higgs fields decay into the black and the white particles. No, it's just the opposite. The black and the white particles come together and start spinning. All right, this is my claim. The only particles that exist are the white particles and the black particles. They call them the white bosons and the black bosons, and call them anything you want. But the white one is the electron neutrino and creates electron showers. The black one never changes. It's a fixed particle. They call it the muon. Between those two particles, when they're separated, they're separated. And you can only separate them through the Venturi or atomic bomb, cosmic radiation, something like that. When they come back together, that's when they form the Higgs fields. They claim the Higgs fields decays to these other particles. That's wrong, totally wrong. These two particles come together to form the Higgs. Now, so when these two particles are together, the black and the white, they form what you call a gluon, the black and the white one. And it's an electron neutrino and a muon neutrino together, the black and the white. You take two black and whites together and you make a photon. That's it. That's all that exists. All these other things here are just flavors of these. And the only two particles that exist is the black and the white one. They can be separated or they can be together. And then they can be together in a four-banger, and it's stable, which is a photon, and then they start to go up into these, which is your periodic table, and they only become stable at certain big quantities. And these are big quantities. These are not little quantities. These are not little quantities at all, because every proton is actually 1,823 dipoles. All right, so this is just instead of one, it's 1,825 or so, because you get to throw an extra couple in there to make it stable. And all of these are just quantities higher and higher. Every proton is 1823. Every neutron is 1824. So by the time you even get to helium, which is the next one from hydrogen, you already have almost 8,000 particles. It's not just 4 or 6. It's 8,000. All right, so this is not, it's just everything's wrong. That's the bottom line, everything's wrong. So we got to start over. We got to have a new periodic table which accounts for the correct atomic weights. Basically, that's the key. It's the atomic weights, and the only reason that it makes a big deal is because we know that each one of these weights is just one more electron. It's not just a chunk here and a chunk there, a strange and an up and a down and a quark and a bottom and a dit. And now they got so many names, it's just unbelievable. And actually just nothing more than it's made of those black and white particles, which is, you call it the Dirac neutrino if you want. Because it's this particle. These are it right here. And we know we can separate them. And we know we can separate them way down into black all by itself and white all by itself. And that, my friends, is what you need to run your car. It has no weight whatsoever, and it has all the energy. Well, all right, what haven't I shown you? I showed you the blue spinning and drifting, and I can prove that it spins. If we were looking down this, it would be like looking down this. The blue is spinning just like the green is spinning, just like the red is spinning. And all it means, the difference in the colors, is the length of the spin. The blue, as I showed you, is way tight. The red is way far apart. That's why the blue is right up tight with each other. See, this is, I think I showed you this already, but it's right up here, zzz, slowing down. The green, the red, watch how far it is apart from the red. It's way out like this. Here it is right here, you see? It's way, way, way out here. These are the distances. Now that's and then the green is right in the middle. Well, the green is very, very fast too compared to the red. The red is just slow, just a slow moving particle. All right, this hopefully will make it more obvious. This is light of the green and the red. The red is much weaker than the green because of the spin. Now, this literally is the spin rate. So if we're coming in from this direction and we're going very slow here, if we were up here going really, really fast, what happens is at a certain point in the ultraviolet range, you get what's called the ultraviolet catastrophe. And at that point, you lose all your white particles, and all you have is the real deadly ones, the X-rays and the gamma rays. And up here, they're subatomic particles. They're in the atomic range. You see it? Back here, this is a visible spectrum. It fits in this little tiny spot right here. Below that is heat, microwaves, radio waves, and these are the very long ones. So in other words, here we are down here. There's these waves down here. They don't have much energy. They get the bump, but a bump, but a bump, but a bump. But when they get up here, they get spinning faster and faster and faster and faster and faster and faster and faster. It's like you going ding, 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 zoom. And then when you get whacked with that, it's a zoom. This is a bing-a-bong. This is a zoom. Okay, you got the zoom? All right, this whole idea about light not slowing down is just, it's crazy. This is light coming out of the sun. Everybody knows the light comes out of the sun. This is a solar eclipse, so the moon is in front of the blinding light of the sun. So we can see where all the rays are going. And I can tell you that there's a lot of things people are going to miss here. These little red spots means that the sun is spinning this way, moving that way. And these are the impact zones. This is the trailing zone. These are the poles right here. So the sun is spinning this way, moving that way, creating these extreme magnetic interactions versus this sloughing off. All of it is particles. And those particles come in these extreme high energies, and then they slow down. By the time they get to us, we're in a visible light spectrum, and it heats us up warm. And then there's like lesser waves that are in the microwave and the radio waves, and then they just fall into just little particles. They're just heat particles. They're no longer moving. That's what light is. It's atomic vapor. All right, I was never a very neat student, but I got to the point of the matter. The transfer of energy is from light to atomic vapor. This was in 1970. I wrote all these papers about what's going on with light and the intermolecular forces, and everything is dipoles. I had it back then, two types, dipole to dipole interactions. There's polar and non-polar, but they're all dipoles. There's no such thing as one big polar particle. All dipoles. And I mean, I did a lot of this stuff. Like I said, I wasn't very neat, but I got the job done. And nobody could handle the outcome. So I went on my own and did something else. And it worked out for me, but didn't work out for the rest of the world. We should have had free energy long ago. That's my take of this. I'm going to tell you right now. And it ain't bragging if it's true, and it's true. I did all this stuff, and that's exactly what I came up with, was that it was all dipoles, which it is. And to get somebody to listen, for 10 years I've been showing this. Every bit of this evidence I just showed you, 100%, I presented to Fermilab, to CERN, to everybody. Lawrence Livermore, JPL, NASA, Yale, all of the different universities. So what do you do about that? I don't know what I do. I just keep showing it, because this is what's going on. Our atmosphere is scrubbing. It's thousands of degrees out here because it's scrubbing as we rub through all these particles in space, which is that quantum foam. It's scrubbing, which creates enormous amounts of ions, which is all nothing but electrons, all by themselves, in that one layer, and it's hotter than hell. And then right below it, it's colder than cold, because it's the dipole nature, the hot and the cold, they work together. And Yale come out with some big paper about, we don't have to worry too much because it's getting colder down here. Well, that's because it's getting hotter up here. It's going to get colder down here, and then it's going to get hotter down below, and that's where we are. It's cold, it's hot, well, it's cold out here, and then it's hot, and then it's cold, and then it's hot again, and that's where we are. That's what's going on. Well, I suppose I've shown you about everything that I need to show you, and that's just the way it is. And like I say, here it's hotter than hell out there, and then it gets cold, and it's getting colder because it's getting hotter, and then it gets hotter below. The hotter it gets out here, the colder it gets just below. The colder it gets down here, the hotter it gets below that, and that's where we are. And the sun's got the same thing. The sun on its surface, it's only 10,000 degrees. Out here, where it's scrubbing its atmosphere, it's millions of degrees. That's the corona. Nobody can explain this. Nobody can explain either one of these. And they just, How do you explain getting from 10,000 here to millions out here if there's just nothing out there and it's just floating away? It's scrubbing. And we are scrubbing because the whole Earth, the whole universe is completely saturated with these light particles, which have slowed down to a point which they are now background radiation. All right, it's just floating around out there in space. And we have to scrub through them.